Hi guys, welcome back. It's Mrs. Webb here. I want to chat with you guys today about catch-up problems. So we're going to talk about catch-up problems today with respect to uniform motion, where the objects are traveling at a constant speed. We will look at these types of problems again later on when we get into uniform accelerated motion, but we're just going to touch on them today and then practice a little bit when we get together. So I have two example problems that I want to run by you guys. Thing to note with a catch-up problem is that it will always relate to objects that are traveling, and they're either traveling in the same direction and one object catches the other one, or they could be traveling toward each other and we want to know at what point they will meet. And like I said, it could be uniform motion, it could be uniform accelerated motion. One object could be traveling at uniform motion and the other one could be traveling at uniform accelerated motion. But right now we're just going to talk about that uniform motion scenario. And I know you guys have looked at these problems in your Math 10 class, but now we're going to look at them in terms of the physics side of things, and we're going to define these problems with our physics variables and our speed equals total distance over total time equation, which is specifically our uniform motion equation. So I've got two examples here. The thing to note with with any catch-up problem example is that you're going to be relating the rate of motion for each object, and the way we're going to relate each object to each other is either the times, that total time for both objects is going to be equal, or the total distance for both times will be equal. And in that way we can equate both equations to each other. Okay, so I've got an example for you here, and this example has Bill. Bill is 35 meters away from Tom, and both men are walking in the same direction. Bill walks at 1.65 meters per second and Tom walks at 1.85 meters per second. So what we want to know is, from where they started, how far does Tom have to walk before he catches Bill? And with these problems, guys, it's really beneficial. I know I've said this before, but it's really beneficial if you guys can set up a bit of an image for yourself or kind of picture it in your mind's eye. I like drawing my images down. So I have Tom is right here. He's 35 meters behind Bill, right? So they're separated by a distance of 35 meters. Here's Bill. Bill is walking at 1.65 meters in this direction, and Tom is going to be walking slightly faster at 1.85 meters per second squared. And eventually he'll catch up to Bill. And I'm just saying that point where they catch up is going to happen somewhere over here. So I know that this separation is 35 meters. I know that in that time that Tom is trying to catch up with Bill, Bill will have walked this distance. So I'm calling that distance Bill. And then in terms of Tom will have walked this entire distance to catch up to Bill. Okay, so that's kind of the scenario, that's the setup. Now we're going to start looking at our variables. So in terms of Bill, I know that Bill has an average speed of 1.65 meters per second. I don't know how far he travels, and I don't know what his time is before Tom catches him. In terms of Tom has a speed of 1.85 meters per second. And what I do know about Tom, I don't know his total distance, but what I do know is that Tom is going to have to walk the same distance that Bill walks, plus that additional 35 meters, because he's 35 meters behind Bill right now. And then again, I don't know that time that Tom takes to catch Bill. Now, remember that I said earlier, in order to equate these two people to each other, we're going to have to either look at time being equal or distance being equal. Now in this case, we know that distance is not equal because Tom has to walk the same distance as Bill plus an additional 35 meters. So distance between the two isn't equal. But what is equal is the time. If I was to start a stopwatch as the observer. And I'm watching, as soon as Tom is 35 meters from Bill, I start a stopwatch, and I keep that stopwatch going until Tom catches Bill. That time is going to be consistent for Bill walking his distance as for Tom walking his distance. So we know that for both Bill and Tom, those distances are going to be equal. That's what's going to link Tom to Bill. So I'm going to set up my speed is equal to total distance for Bill over total time for Bill. And then I'm going to set up on this side my speed for Tom is equal to his total distance over his total time. Now, I know that the times are equal, so what I want to do is I want to isolate for the time, for time Bill and for time Tom. So I'm rearranging my formula, and I get distance Bill over speed Bill and distance Tom over speed Tom. Now, because I know Tom's time and Bill's time are equal, I can therefore say that distance Bill over speed Bill is going to be equal to Tom's total distance over Tom's speed. And I know that Tom's total distance is Bill's total distance plus that additional 35 meters, right? Now I'm going to rearrange this, because if you notice what I have here, I have distance, total distance for Bill on both sides of the equal sign. So I'm going to rearrange that so I can get that distance for Bill on one side and I can isolate it. So I'll multiply both sides by Tom's speed, and I'll multiply both sides by Bill's speed, which gives me speed Tom times total distance Bill equals speed Bill times total distance Bill plus 35 meters times speed Bill. Okay. Now, in order to get the bills, the distance bills on both sides, I'm going to subtract this term to the other side. So I'll get my Tom speed times the distance for Bill minus Bill's speed times Bill's distance, and that's equal to 35 times Bill's speed. I'm going to factor this total distance from Bill out. So I'll get total distance Bill times speed of Tom minus speed of Bill equals 35 meters times speed of Bill. I'll divide this entire term in the brackets to the other side, and I get that the distance Bill covers is equal to 35 meters times Bill's speed divided by Tom's speed minus Bill's speed. And I'll sub my numbers in with the units, and I solve for distance Bill, which is 288.75 meters. Okay. Now, I want to know what is the distance that Tom covers, right? So that was the original question. What is the distance that Tom has to travel before he catches Bill? And I know that Tom's distance is going to be that distance that Bill covered plus that 35 meters. So the 288.75 meters plus 35 meters. And I get that Tom travels a total of 324 meters before catching, or by the time he catches Bill. Okay, so that's a typical catch-up problem, very similar to what you guys would do in math, but now we're looking at it through a physics lens. And note that there's definitely many ways to solve these problems. This is just one of the ways, but regardless of how you're solving, you need to make sure you're being implicit in your explanation of the problem. You're being very linear sequential in how you're solving. You're using all the physics terminology. And in the end, you're getting the answer that we're looking for, right? Second question is just slightly different. So this question, we have a mosquito flies toward you at a velocity of 2.4 kilometers per hour east. If the distance that separates you from the mosquito is 35 meters, at what point, distance and time, will the mosquito hit your sunglasses if you are moving toward the mosquito at 2.0 meters per second and the mosquito is traveling in a straight line? So the thing to note with this that kind of throws you off is that they're giving you the directions for everybody's speed. And really, we don't care about the directions in this problem because the direction is really just there to tell you that these objects are moving toward each other, right? So if I set up my little diagram here, I know that the separation between these two objects is 35 meters. They've given me the speed of 2.4 kilometers for the mosquito. So I've converted this to meters per second, which is what my speed of the mosquito is, 0.6 meters per second. He's traveling east. My bike is traveling 2.0 meters per second west. So all that means is they're traveling toward each other. I don't really care about the positive, negative Rosetta in this case. I know that at some point here, these two are going to collide with each other. So that's my point of splat. And the mosquito will have traveled a distance m, and my bike will have traveled a distance b. So I know that for this particular scenario, that total distance that both these objects will cover, if I sum the distance of the bike and I sum the distance of the mosquito, I will get 35. I know that that's the total distance that they'll cover. So what I'm going to do in this case, and again, there's many different ways you could solve this, but what I'm going to do in this case is, because I know that this is true, that the total distance is equal to the distance of the mosquito plus the distance of the bike, I'm going to isolate both of these uniform motion equations for distance. So that means that my distance of the mosquito is equal to the mosquito's speed times its time, and my distance of the bike is equal to my speed of the bike times the time. And now I'm going to put these terms, these speed time terms, into this total distance equation. So I get total distance is equal to the speed of the mosquito times the time. Speed of the bike is equal to my plus my speed of the bike times the time. And remember that the time is going to be equal for both of these guys, because if I were to start a stopwatch right at the point where these two objects are 35 meters apart from each other, the time that it takes them to run into each other is going to be equal whether I'm looking at the bike or looking at the mosquito. So I'm going to factor this time out, and I get time times speed of the mosquito plus speed of the bike is equal to total distance. And now I'll isolate for the time. So I'm going to divide the speeds over to the other side, plug my numbers in, and I get 35 meters divided by 0.6 repeating meters per second plus 2 meters per second. And my total time, or my time before impact or at impact, is 13.125 seconds, or 13 seconds. Okay, so that's how long it takes these guys to run into each other. Now, in order to figure out the position, I'm going to take this time and I'm going to put it back into my distance equals speed times time for the mosquito, and distance equals speed times time for the bike. And you'll notice I get 8.7 meters for the mosquito. I get 26 meters for the bike. And if you notice, the sum of these is my 35 meters. So they'll collide after 13 seconds, and the mosquito will have traveled 8.7 meters, and the bike will have traveled 26 meters. Okay, so those are two examples of catch-up problems. We're going to work on some catch-up problems when we get together. And again, this is kind of just the entrance to the catch-up problems. We'll see these again when we get into our uniform accelerated motion. So have a look at this, give it a shot, see how it goes. If you've got questions, let me know. Remember that this is just one way to set up the problems. I'm sure you guys are going to find other ways to set up the problems. But like I said, as long as you're implicit in your explanation, you're very linear, sequential in how you're setting it up, you're using all the physics variables, and you're explaining your work as you go, that's all I'm really looking for. So I hope you guys have a great night. Take care of yourselves, and we'll talk soon.